So the result of all that experimentation is what we call Coulombs Law. So Coulombs Law relates force due to electric charge. So it relates electric force to the electric charges. And we can actually guess some aspect of this Coulombs law. We are going to say, at least to start, we'll try to say this electric force is proportional to some combination of quantities. So, when you look at here, what do you think electric force would be if there was no charge at all? Then 0, right? And as you increase the amount of charge, can you imagine electric force increasing? Right? Okay. So what I want to say is that this electric force is, to start out with, proportional to the amount of charge. Right? Now, when you start thinking about the amount of charge, it actually, it's not just one charge that you are thinking of. Imagine that one pith ball had an electric charge, but the other pith ball didn't. Will there still be electrical interaction? So it's, yeah, and it turns out, so the electric force is always force between two charges. So if this has 0 charge at all, then no electrical interaction. So they both need to have some amount of charge. So electric force is proportional to, not to one charge, not to the other charge alone, but it's proportional to product of the two charges. So more charge collectively means more force. And you guys saw the dependence of electric force on distance. So we are going to come up with some functional form that makes the force go down as the distance increases. Any guesses what that form might be? We're just guessing. People had to do experiments to find this. I mean, you might know this from your earlier science class, but, Yeah, you're saying K right now, so you're just telling me what Coulombs law is. I want to get to that, because unless you have it memorized to start out with, I want to make sure that this law makes sense to you. Having it memorized and having it make sense to you is two different things. So we took care of the charge portion, and we are going to take care of the distance portion, and we are going to eventually move on to the constant between them. So, so how do you think it should, just taking a guess, not memorize the version of Coulombs law, how should it depend on the distance? So if we put the distance on the denominator, that's one way of having it, having the force go down as distance increases. So, you might guess this as the form, proportional to product of charges and inversely proportional to the distance. Turns out, experimentally, it's a distance squared. So this is the part that you can't quite guess. You have to know this experimentally. Right? Now, in all the laws of physics, the goal really isn't to remain at this proportionality relationship. We really want to get to some expression where we can say this force is equal to some set of expressions here. But when you look at it, there's one major obstacle here. Anybody here know what the major obstacle here is? This, by the way, is why we emphasize dimensional analysis so much in Physics 4a. But it's not until Physics 4c that you see true value of dimensional analysis. Units are all wrong. Here, the units are newtons. Or, it's force, right? So in the basic SI units, these newtons would be kilogram meter per second squared. Anybody here know what the units on the right-hand side are? Yeah, it actually gets a little bit complicated because we have these charges. Anybody here know how to express a unit of charge in terms of kilograms, meters, and seconds? Turns out within the unit system of SI system, you can't. There are unit systems where you can. It's called Gaussian units or sometimes CGS units, where you do define unit of charge in terms of these, but they involve ugly square roots or whatever. We're just going to stick to SI units. And in SI unit system, we actually define a new unit just for charges. So even though it's still totally true that three quantities define the basic way of measuring things in physics, to make things more convenient, we're going to introduce a unit of Coulomb. So the unit of charge, we name it after Coulomb, who did a lot of work. So these charges come in units of Coulomb, or capital C. So the units on the right-hand side so far are this. It's a Coulomb squared per meter squared. Do these look like the same units? Nope, not at all. So how do we fix this so that we can say the left-hand side is equal to the right-hand side? Crystal? Sorry, could you say it louder? I couldn't hear. That doesn't help, because if I divide both sides by Coulomb squared, on the left-hand side, I'll have Coulomb squared on the denominator. So I'm just modifying my equation. So I mean, that's essentially what we are doing, but we want to do it in a systematic way where it's not just, I don't like these coulombs, I'm going to get rid of it. Like, that's not how we want to do it. We want to make sure we understand where it's coming from. Maybe let me build your intuition this way. Where else have you seen a similar expression before? You have force on one side, and on the right-hand side is an expression that describes how that force can be obtained. And actually, a lot of these have a very similar feature to that other equation or law that you might have seen before. Newton's law of universal gravitation. So as a reminder, this is what it looked like. Newton's law of universal gravitation, force on the left-hand side. On the right-hand side, it's proportional to the product of masses. Mass 1 times mass 2 over distance squared. So when you look at the units here, you face similar problem. On the left-hand side is unit of newtons. On the right-hand side is unit of kilograms squared per meter squared. How do we fix this? Yeah, there's a constant, gravitational constant G. And this constant, it does two things. One, it gives you the exactly correct unit so that you can now say this equality. So this G, without knowing anything else, you can say this G must have these units. It must have unit of Newton times meter squared per kilogram squared. So, Crystal, this is how we cancel out the unnecessary units here. But we do it by including it into this constant. This is the systematic way of doing it. And this G has a very particular value. You can look it up in the textbook. It's one of the things about G is it's a very small value, right? So, because Coulombs law really reminds us of Newton's law, in fact, it's in this inverse square relationship where it really reminds us of Newton's law. We are going to take the similar approach. So we are going to introduce a physical constant here that for the time being, we are going to call it K. We are going to call this K, not to be confused with the Boltzmann constant. This is a constant that we are going to use only for a short while, and eventually we'll replace it with something more fundamental. But, so we need a constant here to make the units come out right and to have the correct number. So what should the unit of K be? Yeah, I need the newtons. Anything else? Yeah, meter squared per coulomb squared. Yeah, So this is how we get rid of this unneeded or unwanted unit of coulombs. But by we do it not, not arbitrarily, but by including into this physical constant, we can try, or people have done experiments to find the value of this constant experimentally. And if you want to look up this constant in your textbook, you will find that you cannot look it up directly. What you need to do is, does your textbook anywhere tell you this fact? It does not. It ought to. So your textbook will not list K. I mean, it does list K, but that's Boltzmann's constant. Don't be confused with the Boltzmann's constant. So later, I will justify this better later. The way this K is expressed in terms of constants given in your textbook, this is equal to 1 over 4 pi epsilon naught. This epsilon naught is what is listed as permittivity of free space, or it's an old-fashioned term. You can sometimes just say electric constant. And when people say electric constant, they mean this epsilon naught. All this strange combination, to explain it, I really need the Gauss's law, which we'll get to next week. But we can plug in numbers and just have a sense of how big or small this number is. So let me plug in the numbers. This is 1 over 4 pi times epsilon naught, about 9 times 10 to the minus 12. 9 times 10 to the minus 12, and let me be careful with the units here. Coulomb squared per Newton meter squared. So when you work all of this out, 4 pi is about 12. 12 times 9, that sounds like about 100. So 100 times 10 to minus 12, that's about 10 to minus 10. So this is going to be approximately 10 to the 10. And working at the units, it's 10 to the 10 times Newton times meter squared per Coulomb squared. Is the unit what we expected? Yes, I mean, it should work. And so the number that goes with that unit is approximately 10 to 10. I think if you do more exact calculation, it's like 9 times 10 to the 9 or something like that. Is that a small number or a big number? It's a big number. That's one of the features of electricity, that this constant that occurs here, it's going to be a pretty big number. So when you look at charges, so we introduced the Coulomb as the basic unit. You will find that 1 Coulomb is an unreasonably large amount of charge.